Random walk. The study of random walk is important to understand various phenomena starting from physics to finance. To understand Brownian motion, to understand protein folding and many problems. Here in this talk I will discuss about how we can create random walk in 1D in this particular video, and I will write code with Python. Okay, so let me generate a random walk in 1D. Suppose here is a line, one dimension, and the walker is here. The walker starts from here, and suppose these are the step size. These are the equal step size on two sides. You start from anywhere, and the walker randomly goes from this position to either right or to left, either right or to left. And it's suppose it arrives here in on the right, and then again there are two possibilities. Either it will go right or it will go left, and in this way it will after some time interval it will arrive somewhere. It will either reach somewhere on this right direction or somewhere in the left direction. And if we imagine that the each step is one, step size is 1 and time step is in unit time, so the right side is if it is 0, then this is right. To go to right side is say +1, and to go to left side is a -1. And again from some position on the left, say for example, to go on the right is gaining this on the one step size +1, and to go on the left side it's the -1. So I'll first generate these sequences of +1 and -1 in computer. Well, it's very easy. If you call a random number from say numpy, then it is just a random number generator which will create random number from -1 to +1. So I will do it with numpy. So import numpy as np, right? And and now I create the random numbers. So np dot random dot randint. Randint is the random number generator, integer random number generator, which will generate random numbers from the lower value to upper value. So if I write some 0,2, it won't touch the upper limit. It will create random numbers between either 0 or 1. So let's see that. Run it. It will create 1. Let again run it. It will 0. Again run it 0. Again run it 0. Again run it 1, and so on. So we can also discard the 0. We can only write 2, because by default the initial the lower limit is assumed as 0. So it will be automatically assumed from 0 to 2. So and now I can write through keyword argument size equal to say for example 10. That means I want to create 10 random numbers, either 0 or 1. So it's an array, 1D array of 1s and 0s. Okay. Now since to create the one-dimensional random walk, I need +1 and -1 to indicate that either the particle is on the move on the right side or move in the left side. That means on the positive side or on the negative side. So what we can do is that we can multiply this by 2, since it is an numpy array, so each number will be multiplied by 2, so it will be either 2 or 0, and then I can subtract -1, so the numbers will be nicely +1 or -1. Okay, so notice one thing, that we are clicking every time and the different sets of random numbers are coming up. So you want you can the initial random set, array is not there. Okay, so every time I do this, I create a set of 1 and -1. Okay, so this is the array, 1D array. So now what we can do is that the worker is moving from a position right left right left right left, and somewhere it will reach. So I want to know what is the cumulative sum. That means it will the ones, plus ones and minus ones to be added. Okay, subsequent plus ones and minus ones, so it will be the cumulative sum. So if you do the cumulative sum, so there is a function called cumSum. If we put this in this thing, okay, let me write it as x, sum x. Okay, so let me write it as x, and if we write np.cumSum x, it gives me the values. It started from, say, first it was -1, then -2, then -1, 0, 1, 0, and so on. So if we say take, say, 1000 random numbers, of course it will be this array will be the array of this see, suppose it's somewhere negative and then some positive. It is for one configuration. If we do it again, it will be something else. If we do it again, it will be something else. So the end result may be positive or negative or so on. So it will go on. So this is one random walk. This is the one random walk. If we want to plot this, so we can plot this with matplotlib. Import numpy as np, and then plt.plot, and suppose I call it, say this is the x sum, or some, say, xx. Okay, so it's called xx, and we plot this xx. I don't need another coordinate because it will automatically plot with 0, 1, 2, 3, 4 and this way. And so I will see sorry, it is import matplotlib dot pyplot as plt. So if I do that, so it will start from, say, 0 and then -1 and then something, and then it will create this random walk. Okay, if we do it again, it will be another walk, another random walk. Basically this is the cumulative sum, sometimes negative, sometimes positive. We do it again, and we get another random walk. So we have we can generate many random walks, and what we can do is that we can take some kind of configuration average, but configurations are, each such walk is a one configuration. Okay, we start from, see, initial position and allow for some time to the walker to move somewhere, either on the right or left directions each time, and then this way we create one configuration. So we should actually, to have some statistical sense, we should have actually average over all these configurations, but normal averaging will not give you any sensible thing, because these are plus and minus sometimes. So we'll take square of those things, and then we take mean of those things or average, and then we can take root. That means we will actually look at the root mean square values. Okay, so here let me start from here. Okay, suppose you are the configuration is, say, n is the number of configurations, and t is the total number of time. Well, so n is say 10,000, and the how much time, say it is 1,000 times, say for example total time is 1,000. So actually we will generate 10,000 such walks, and each walk is 1,000 unit time long. Okay, so I write nt equal to 10,000 comma 1,000. Good. So let me create the range of time. We will need it, so I can call it time t, the successive times, range of 1 comma, I can write as t plus 1. You can write it in your own way, so that it will create time from 1 to t. That means 1 second, 2 second, 3 second, for example, to 1,000 second, because that's why I write t plus 1 here, because the range will create numbers between 1 to t. Well, so let me run it. Now I create the walks at one go. Okay, so let me write this as walks, the variable name, then 2 star np dot random dot randint, and then 2, and then in place of size we can actually create 10,000 random walks, and each random walk of length 1,000 at one go. That means we can at one go we can create n by 10 matrix or 2D array. So we can write n by t. That means the n rows and t columns, right? And well, and I write it as -1. Okay, so this 10,000 random walks, and each random walk is 1,000 unit long, and the numbers are -1 and +1. I just create that. Okay, walks, we have created those walks. If I want to see what it is, so it is this. So it's a 2D array. So this row is one random walk, this row is another random walk, this row is another random walk, and so on. And if we go by columns, this is the time 1, time 2, time 3, and up to 1,000 time. This is also time 1, time 2, time 3, etc., etc., etc. So we have a 2D array where if I come along the columns, see the first column or the 0th column is the time 1. So next is the time 2, next is the time 3, and so on. So these are the walks we have generated. Now we need to calculate the cum sum, that means cumulative sum of these walks. That means along this array, along this row, along this each row, I want to calculate the cumulative sum, that means successive values. Okay, so you have to add on these values. So we want to take cum sum on each row. How do I do that? It's very easy in NumPy. We can write np dot cum sum, and I can very well use the mechanism of the axis. I can write walks. That means I want to apply this cumulative sum, this function, on these walks, okay, on the 2D array, but I want to create the cum sum, that means cumulative sum, along this axis, and we know this axis is axis equal to 1. if we go from left to right or right to left. Okay, east to west is axis 1. So we write axis equal to 1. Okay, and suppose we call it some other variable, positions. Okay, so let me check. Okay, done. Let me also plot these positions. Okay, so this is the first row and the cumulative values. That means it is one random walk, this is another random walk, this is another random walk, and so on, and each is starting from 1 unit time 1. Actually the 0th time, this is the 1 time, first time step, the second time step, and up to 1000 time step. Now what we will do that we want to actually take the squares of all those things also. So let me also write another variable, position square, for example. So I write positions and star star 2. That means I square all the values from on the rows and columns everywhere. So I actually calculate the square of all those values. Then I want to take the mean. What do I do? I want to take np apply np dot mean. So np dot mean is again the numpy method which will apply on this 2D array, and I can put axis. So every numpy method has the provision of giving axis, so you can apply it on any dimensional array. So if I write np dot mean and then position square, this one, and then this time I will calculate the mean of those first time, mean of those second time, mean of those third time. That means we want to create the mean along the, they apply the mean along the columns. So that means I write simply axis equal to say 0. Earlier it was axis equal to 1, and now I want to come down through columns, up down, right? So it is axis equal to 0. So this is the mean I have calculated. So let me name it as say mean underscore position underscore square. That means square and then of the position and then mean. Okay, so this this is this, well, and also I want to now calculate the square root of those, so which we call RMS, root means square. So let me write it RMS equal to np dot square root, and now we don't need to give any axis because it will be square root on every element. So np dot square root and then mean and then position square, this square root of this variable on this value. Okay, so well, so I run this, done. So now if I want to plot plt dot plot, I want to plot this time versus RMS, right? This is the time this I created this range to plot just like that. Okay, so if I want to plot t versus say RMS, of course that is not needed. We would not need that also, because automatically the x-axis would start from 0 to say 999 or something. But okay, for our satisfaction we write t versus RMS. So let's see how it behaves. So here it is, and you remember this is the mean of many some configurations, square of the mean of the squares of the cumulative positions, and I want to see how this behaves. Okay, so I can fit it with I can plot it with some bullet symbols, but there are so many points that you will not really understand, but of course we can plot like every say 10 points we can plot every 10 points. So I can slice it like this. So start from the beginning, end at the end, and the with step size 10. That means we are actually plotting every after every 10 values. Okay, so in that case it will be like that. Even I can write it as 20 because there are so many points we are generating, 1000 points. So it will be all the points you can see. Well, now since we know that from theory that this is actually this RMS actually goes as t to the power half, right? So basically we know that this RMS value, this RMS value goes as t to the power half. Okay, so if we take the log of RMS, of course, so it will be something plus half log t. That means beforehand we from the beginning, if we take the log of this and this, it will be straight line and it will be easy to understand really. So what we do is that next let me write t equal to np dot log of t. That means I take the log values of all the time scale, okay, time scale log, and then RMS is actually log RMS. So I can write np dot log RMS. Okay, so let me run it, and now if we plot it, plt dot plot versus t versus RMS again, and you will see this will be really a straight line. So how good it is with theory we'll understand, because now we want to actually say fit this data and to find out what is the slope. The slope should be half, okay, 0.5. Oh, let me plot it with some bullet points. Okay, so of course this is a log scale, so initially we'll have not many data, and the from the upper end we'll have all the data points squeezed. Okay, since it is a log scale, we could actually fit the original curve also, but okay, suppose we plot this log data. So now I fit this log data, okay, log scale data. Okay, so it's a linear fitting. We can fit easily. We can fit from there is a module in NumPy called Polynomial. Under that there is a module called Polynomial, and there is a function called polyfit. So easily we can quickly fit with that. So let me import NumPy dot polynomial dot, inside that there is polynomial and as poly. We have to see whether they sometimes change the modules. Okay, we have to see the locations of the modules. So when we did that first, it was like that. Let me check whether it is there. Okay, it takes, that means it is there. So under NumPy there is a you can call this a module polynomial, and under that there is another sub module called polynomial, and I rename is at local name as poly. So if we now write poly, and inside that there is a function called polyfit, that means it will fit with a polynomial. So if we fit in the linear scale, it is also a polynomial. Okay, polynomial of order 1. So what we have to give, the x-axis, that means t, the y-axis, that means RMS, the values of x and y ranges, and you have to tell the what kind of polynomial you will fit with. So I will fit with linear polynomial, that means of degree 1. Okay, so poly.polyfit t rms1. Oh, yes, and you have to remember that these are the log values already. Okay, so I let me uh, run this. You see, it creates an array. It gives me back one the array. The array is so this is the slope and this is the intercept. Okay, so y equal to mx plus c. It writes is c plus mx. Okay, in that way. So first one is that is the intercept, and the second one is the slope, and you can see the slope is already 0.49 with say 10,000 configurations and for 1,000 time steps. Okay, you can do it better with taking many configurations and for large time. Okay, so this is the these are the numbers. Well, I can write this as say coefs. For example, I write it as the coefficients. Okay, so I store it in coefs. So now the coefs is the array of these things. Okay, let me clear it. Okay, now I want to call the poly val. That means it is a polyfit, and I have to generate the values of the y axis, y values, because I give t, that means x values, and I give the coefficients, these coefficients. That means it will construct the RMS, true RMS values. These RMS is created by me, and if I now give the x axis, that means t, and the coefficients generated from the polyfit, it will create the polyval function will create the array of the y values, that means the RMS values. So let's see what it does. Okay, so it has created all the y values. Okay, so I can write it as RMS say fit, that means the fitted value of the RMS. Okay, this is the RMS value I create, and this is the RMS fit, the actual fitted value with this linear this polynomial. Okay, so let's run that. Okay, now I want to plot again plt dot plot, and I want to plot with t and RMS. These are my the original values, and I want to plot with bullet. Okay, and well, and also I want to plot with t again, or maybe I will plot with another with plt dot plot, and then again t versus RMS fit. If I don't say anything, it will fit with the line, continuous line, and it will fit with the gorillas, that means with bullets. So for clarity, I take say not say values after each 20 in the gap of 20s. So colon 20 and so on, and this. Okay, let me run it. So here is the fitting. So the line, the orange color line is the polyfit line fitted by the polynomial of this whose slope is close to 0.5. It shows it is in the coefficients, inside these coefficients, and there is an intercept also. Okay, and these are the bullet points are the simulation we have created through this random walk program written in Python. Okay, so that's it.